So first I'll show the input vectors and the mixing function. So let me see. Yes. Yes, so these are the, this is the mixing, or this is the compression round. So in Blake, we have 12 rounds of compression, and we have, as I said, these input state vectors, which are this V1, V2, V3, and then we mix them with these message chunks, and this goes on for 12 rounds. So this is where the mixing function is called, and then then we achieve compression. So inside the mixing function, we have these operations. So you see that all these elements, we either add them or do some XOR and rotation. So these are the most expensive parts of the circuit. So addition is not a big deal, but for XOR, rotation of the bits, if we go about doing it bitwise, it's going to be a long circuit and it's going to be a disaster. So to achieve this, what we do is we implement like a spread table. So we don't do like a bitwise XOR. We use something called spread. So a spread function of a bit is you just interleave the bits with zeros in between. So suppose we have a bit as 1, 0, 1, and to obtain the spread form, we just put bunch of zeros, 1, 0 in between the bits. So this will be 0, 1, which is the original bit, again 0, which is the interleaved bit, and 0, which was original, and then again 0, and then again 1. So between our original bits, we input we interleave these 0 bits, and now something so why we use spread for XOR? So suppose we want to do XOR between two elements, 1, 1, 0. We just obtain again the spread form of the element, and to do the XOR, we just simply add them. So we just simply add them. This will be 1, 0, 1, 0, 0, 1, and we take the even position bits for the XOR. So here we just put this in spread, take the addition, and take the even bits to compute the XOR. And why this is efficient? So also one more thing. So to do XOR in like a circuit like Blanc or Halo2, we implement lookup tables. And the size of lookup table determines the the cost of the circuit or cost of a lookup for each bits. The number of rows that would contain is 2 to the power 32. So suppose we are doing XOR between 2 to the power 16 bits. The lookup table for bitwise XOR will be 2 to the power 32. So this table just contains all the values, all the 16 bits values, and all the results of these values. And we just do a lookup that, suppose we have 2 bits, what is the result of that lookup? And this 2 to the power 32 rows with, suppose 3 columns, which will have the original bit A, B, and the XOR between A, B. The size of this will be 24 gigabytes. So it's just not practical to store and do calculations with it. But amazingly, if we do like a spread table, so for spread table, we only need 2 to the power 16 rows. And the size of this table is just 356 kilobytes. So it's just dramatically improves the cost of doing XOR in the circuit. And And one more thing. So we have these rotations and XOR, right, in our circuit. So what we try to do is to keep every operation, or to keep all these elements VA1, VB, VA, VB in the spread form. And we use the spread form to do the XOR, and then do rotation, and then take the even bits. So we keep everything in spread. We look up these arguments to the spread table, and at the end, we just take the even bits of the computation. So this will dramatically improve the cost or improve the efficiency in the circuit. So now let's see how this is implemented. So this will be, so again, yes. So the first two operations we have is we add this VA, VB plus X, where X is the message, and we have the second operation as the XOR between these two elements, and then a rotation. So to achieve this, so also one more thing. So in the original input message is 64 bits. So all these V elements, V1, V2, these are all in 64-bit chunks. But to have an efficient lookup argument, we have to split them into 16-bit chunks, so that the lookup is much more efficient. And so all of these elements is decomposed into 16-bit chunks, and then we do these operations. So first I'll show the code for the decomposition. So so this is the, yeah, so this is the decomposition function, where we decompose this message chunk, which is 64 bits, into 4 equal chunks of 16 bits. And we again take both the spread form and the original element form. And once we decompose, we go through these operations, which I talked about, which was the addition and the XOR operations. Yes, so this is the circuit layout. So this is a circuit layout in Halo2. We are doing the first operation, which is VAVB plus X. And the first column is the tag column. So when we do a lookup in the spread table, we constrain our bits. So what does that means is that, say, suppose I am looking up a 16-bit, I'm looking up a 10-bit or a 7-bit number. So I constrain that. So suppose if I look up 7 bits, I constrain the tag between 0, 1, and 2, where the tag boundaries define that we only look up in those bit lookup arguments. So we don't look up like 9 bits, 10 bits. We only look up the 7 bits. So these tags help us with that, and it again optimizes the operations, because we are not going through the whole table. And as I said, we have in the first column, we again store all the chunks, the 4 chunks, and their spread versions. And the same we do for A and then B. And then to add them, what we do is again take only the spread forms of A, which is on A3, spread forms of B, which is A4, and spread form of X, which is A5. And the resultant will be this A1 vector, which has again these 4 chunks, and again the spread forms of the 4 chunks. So here is the code for the create gate. So we are creating the gate. We are assigning all the row columns with the spread variables, and assigning all the correct rotation for each cells. So now let's look up for the XOR operation. So again, we do the same thing. We store all these original bits and spread bits in the table as before. And when we do the XOR, we keep everything in spread, and then we rotate the bits. And at the end, we only take the even bits. So we do the spread version of XOR, where we just interleave the bits, add them, rotate them correctly, and then take the even bits. So this again optimizes the circuit, because if we took the even bits before rotation, we would again have to split them into chunks, but we don't do that. So we only take the even bits after the rotation. So this is the code for the XOR. Yes, so originally we have these 4 chunks. We add them to have the XOR, and while rotation, what we do is if we have M and OP, these are the original ordering of bit chunks, and then we have to do a rotation by 32 bits. So we rotate, because it's in a spread form, we rotate 64 bits because it's double of that. So when we rotate the M and N to the right, this becomes, the first bit becomes O, then P, then M and N. And then we just check the spread witness that the calculation was done correctly, and that's it. Yeah. So now I'll just quickly show up the spread table demo. So I have not completed the Blake implementation, because it will take a lot more effort, and I don't think I'll be able to run it on my computer. So I would have to use compute hardware architecture. So this is the spread table, and what it does is that it has the tag, which is 0, because we are only looking up the 7-bit number, and then the first column is the original dense bits, and the second column is the spread version. So what this table does, it just checks that the dense version is dense and spread versions are correct. It looks up in the lookup table both these dense and spread forms, and then checks whether the computation was done correctly or not. So even if I change the 1 bit, so I change the spread form, so this should give me an error. So let's see. So it says the test failed because, again, the lookup argument between the dense and spread versions did not match the lookup table, and this what was the cause the error. So I think that's it from my end. Thank you guys for